Have you ever wondered how a machine actually learns to play a game like chess? I mean, not just knowing the rules, but developing actual strategy. Well, it turns out the secret to building super intelligent AI is kind of hidden inside these ancient games. We're going to dive into how we teach a machine to anticipate, to strategize, and ultimately to win. And what's cool is the methods reveal the very core of how AI really works. All right, so first up, why games? Why are they the perfect laboratory for artificial intelligence? Well, think about it. They have crystal clear rules, a definite goal, checkmate, and a super simple way to tell if you've succeeded. You either win or you lose. This gives us this perfectly controlled environment to test out some really complex ideas. So the real goal here isn't just to program an AI with the rules of chess. That's actually the easy part. The real challenge is giving it a way to make strategic decisions, a way to look at all the pieces on the board, weigh its options, and consistently pick the move that's going to lead it to victory. And chess is pretty much perfect for this because of three key things. First, it's fully observable. That just means nothing is hidden. All the pieces are right there for you to see. Second, it's deterministic. There's no luck, no rolling dice. A move always leads to the same result. And finally, it's zero-sum, which is just a fancy way of saying, if I'm winning, you're losing. My gain is your loss. It's the perfect little battlefield for an AI. Okay, so let's imagine we're building our first game-playing AI. The most intuitive way to start is with something called a greedy approach. It's a simple idea, but as we're about to see, it has a pretty serious and kind of obvious flaw. A greedy AI is, well, it's exactly what it sounds like. It's incredibly short-sighted. It looks at every possible move it can make right now, gives each one a score, and just picks the one with the highest immediate payoff. It sees a path that gets it a score of 9, and it's like, yep, that one. Simple as that. But, and this is a big but, this is exactly where the greedy strategy completely falls apart. By grabbing that quick high score, it totally ignores what a smart opponent is going to do next. And that opponent immediately sees the opening, makes a countermove, and boom, a catastrophic loss for our AI. It's the classic case of short-term gain leading to long-term disaster. So to build an AI that can actually win, you have to make one absolutely crucial assumption. Your opponent is a genius. They're just as smart as you are, maybe even smarter. This one little shift in thinking leads to a much more sophisticated and way more powerful strategy. And that strategy is called the Minimax principle. The name really says it all. The AI tries to maximize its own score, while assuming the opponent is always trying to minimize it. It's like being productively paranoid. For every move the AI considers, it asks, what's the absolute worst thing my opponent can do to me in response? Then it picks the move that leaves it in the best possible shape, even in that worst-case scenario. So let's see how this actually works. For each of its possible moves, the AI plays out the opponent's turn in its head. It figures out the one reply that would be most devastating, the one that gives the AI the lowest possible score. That terrible outcome then becomes the new, more realistic score for the AI's original move. So remember that tempting move that looked like a 9? Well, now the AI sees that a smart opponent will always turn it into a -6. Not so great anymore, is it? Okay, so now the AI can make a real strategic choice. It's not just looking at the immediate scores anymore. It's comparing the new worst-case values. -7, 0, -6, and 1. And what's the best of those bad options? It's the 1. It's not flashy, it doesn't give a huge immediate reward, but it is the safest, most solid play against a perfect opponent. And that, right there, is the genius of Minimax. So this seems perfect, right? An unbeatable logic for playing a game. But there is a catch. And trust me, it is a very, very big one. Take a look at that number. That is the estimated number of legal positions in a game of chess. It's a 1 followed by 154 zeros. Trying to calculate every single possibility using Minimax isn't just hard, it is physically impossible. Seriously, no computer that exists today, or that we can even dream of building, could ever finish that calculation. Let me put it another way for you. There are more possible ways to arrange the pieces on a chessboard than there are atoms in the entire observable universe. Think about that. To run a full Minimax search would take longer than the age of the universe itself. So how do you solve an impossible problem? Well, if you can't win with pure brute force, you have to get clever. You need a shortcut. And in the world of game AI, that brilliant shortcut is a beautifully elegant concept called pruning. The AI pioneer Pat Winston said it best. If you have an idea that is surely bad, don't take the time to see how truly awful it is. This is the absolute heart of a technique called alpha-beta pruning. It's all about intelligently ignoring huge chunks of the game tree that you already know are just dead ends. Let's watch how it works. The AI starts by going down one main branch of possible moves. It goes deep until it finds a sequence that guarantees it a score of at least 100. Okay, it makes a note of that. 100 is now its baseline. Any other path it explores has to be better than that. Next, it starts exploring a second major branch, but it doesn't even get that far before it realizes something crucial. Down this new path, the opponent can force a situation where the AI's maximum possible score is only 20. The algorithm immediately stops and asks itself, is 20 better than the 100 I can already guarantee? Of course not. And right there, that's the magic pruning moment. The AI knows this entire second branch is a dud. It's an inferior option. It doesn't need to waste time exploring any of the other millions of moves that might exist down that path. It just, snip, it cuts off the entire branch and moves on, saving a truly staggering amount of time and effort.
This basic idea, Minimax plus some really smart pruning, is the engine that powers countless game-playing AIs. It's inspired even more efficient versions like Negamax, and even some pretty extreme pruning algorithms like SSS Star, which might trade a tiny bit of accuracy for a huge boost in speed. But they all come from this same brilliant DNA.
And you know what? This race for computational speed is far from over. The drive to build the absolute strongest chess engine has become this relentless arms race of pure algorithmic cleverness. Modern programs use a whole arsenal of advanced tricks. You've got things like iterative deepening, which cleverly reuses its old work as it searches deeper. They use transposition tables, which are basically a memory system so they don't analyze the same board position twice. And they use bitboards to represent the board in a way that computers can process at lightning speed. It's just a constant battle for more and more optimization. All of this insane calculation actually points to a really profound idea. Way back in 1912, a mathematician named Ernst Zermelo proved that a game like chess is ultimately determined. That means if you had infinite computing power, a perfect game of chess is possible. We just don't know yet if that perfect game leads to a guaranteed win for white, a win for black, or just an unbreakable draw every time. And that leaves us with one last, kind of haunting question. If one day an AI could actually compute that perfect game, if it knew the single best move from the very start no matter what, would it even be a game anymore? Or would it just be the performance of a giant pre-solved math problem? And what does that tell us about the future of strategy, of competition, and maybe even the nature of intelligence itself?